Good afternoon. As I advised last week, for this week I will be at university to get my jab. I'm not entirely sure whether I will be done by 3 or not, so I think it's better to just record the lecture because probably if I go there at 2, I will not be done before 4 the earliest. So I'm hoping that I could do another video, finish off the chapter, and then next week we can actually discuss if you have any problems. As far as I'm concerned, this is actually the last chapter that we have to cover, so then it will just be working a number of questions to help you understand the chapter a little bit more. So, the last group of reactions will be the addition of non-organometallic carbon nucleophiles, such as cyanohydrins, okay? Addition of Cn minus. Now, this mechanism is very simple. It's something that you have done quite a few times before, and therefore you can actually do this. You can actually see that here you are going to have the preparation of a bifunctional group where you have a nitride and an alcohol, and this is pretty much an insane reaction because you are increasing the carbon chain whilst you are not losing functionality. Okay, Cn is a very, very versatile functional group, as is DOH. So, in fact, here they undergo different reactions, and because they undergo different reactions, what you're going to have is the option, the possibility of doing a number of literally different combinations. One of the reactions we're going to be doing in this chapter is the Grignard reaction that you've done at A level. Please keep it in mind because that is something that is going to be very useful, and I'll just make sure that I'll send you another recording, a short recording on linear reagents, how to use them, how to synthesize them, because they're quite useful when it comes to ketones and aldehydes. Okay, but for the carbonyl groups, this is the last reaction we're going to be doing here with regards to nucleophilic additions. Then the last reaction, proper last reaction, will be the addition of the hydroxy groups. Okay, so oxidation of ketones by peroxycarboxylic acids. And here we are going to get esters. So if you use a peroxycarboxylic acid, which is pretty much a carboxylic acid with an extra oxygen between the carbon and the hydroxyl group, you will end up producing an ester. Now, this is a two-step reaction. The first step is the oxygen, the peroxide oxygen reacting with the carbon, and the carbonide extracting a proton. And once that happens, then you have an 8-electron concerted process where the electrons from the oxygen hydrogen form the carbonide. Then the R group shifts to the oxygen. You break the peroxide bond to produce a carbonide and an alcohol. So it would be a carboxylic acid at the end of the day. Now, this step, this reaction is important because you can change carbonyls to esters, and therefore, if you want, you can even break the carbon-oxygen bond to reduce the carbon chain. So, in this situation, you are going to be able to divide the carbon chain into two. And you do not know of a lot of reactions where this is actually common, where this happens. Okay, so I would say keep this in mind. The transition state involves migration of an R group, okay, and this will actually end up being something very useful because you will end up migrating an R group that we haven't done a lot. So you are migrating an alkyl group. We have seen this alkyl shifts, we have seen them in elimination reactions of alcohols, and we have seen them in carbocation formation. So the alkyl shift happens because you have a something pulling, okay, on an alkyl group to make it a molecule more stable. Okay, and that is actually very, very important. Now, this is Reo Selective, meaning it will choose one side over another, okay? And this migratory aptitude, if you have a primary, it's less than a phenol, which is approximately equal to secondary, and it's less than a tertiary. So the group, if you're gonna have a group, okay, is gonna go to the carbon that is gonna be most substituted. Similar to the Markov-Nikovs group, okay, where the cation will be on the most substituted. So even here you can see the same thing. Now, one of the preparations of carbonyl groups is the Wittig reaction, and the Wittig process, the Wittig reaction is a very powerful reaction. The Wittig reaction uses phosphonium salts, okay? And first you need to prepare the phosphonium salt synthesis. And this is done by having phosphine, such as triphenyl phosphine, and you react it with via SN2 with a halogen alkane. And you will end up getting a positive phosphorus. Once this phosphorus, okay, once this phosphorus is prepared, then you can use it in your reaction. And this is the mechanism. So, you need a strong base to deprotonate the carbon. Okay? And this deprotonated carbon will then attack the carbonyl as a nucleophile. Okay? Opening up a carbon single bond carbon. I think I said, if I'm not mistaken, apologies if I did, preparation of carbonyls. This is preparation of alkenes. Okay? But it's a very useful reaction. Once you form the carbon single bond or carbon bond, then you form a cyclic four-member ring between the carbon, phosphorus, and oxygen. But this is unstable, and therefore you will end up breaking the bond. So there are two ways how to break the bonds, but what you would need is that you would want to break the carbon-oxygen to form a double bond between the phosphorus and the oxygen, and the phosphorus carbon to form a double bond between the carbon and carbon. And this gives your final product. Please note that if you do any other bond breaking, okay, you will revert back to your original starting material. And that would be a reversible reaction, and it would not give you the right product. So what I'm saying here is not that I would want, this is the only way that it can do, that it can be done, but this is the only way that it's going to give you a new product. And normally in chemistry, if something doesn't give you a new product, then it's not worth looking into. Okay? Then it's not worth looking into. And here are a couple of examples where you can actually see that this reaction is going to provide, okay, where this reaction is going to provide only one isomer, okay, and this is near highly efficient. Now, highly efficient, you're telling me 66%. Yes, 66% might look low, but if you were to compare it with something like the elimination of halogen alkane, you'll always have a mixture there. So 66% is going to be better. The only problem is that the phosphorus salt, once you use it, it will need to be thrown away because at this point it would then have no other uses. If you have resonance stabilized islets, these would then be trans-selective. What does trans-selective mean? If you're going to have a choice of preparing either a trans or a cis eyelid, okay, it will be trans. Okay, it will be trans. The islets are the phosphorus groups. Okay, apologies because I don't think I've ever explained it. So in the Vitic, the islet would be the phosphorus containing group. So this is the islet here, this is the islet. Okay, and an islet, as far as I'm concerned, it is when you have a charged group. Now, here is being shown as C double bond P, but you can also know them as C negative and P positive. So you have double charge next to each other. And once you do that, once you get such a compound, you can form the double bond, but the phosphorus then would not obey the octet rule. So if you were to look at the phosphorus here, this has 10 electrons, whereas this has 8 electrons. And to obey the octet rule, it's normally a bit better. So if you have an eyelid, it will normally join through the trans group. Okay? And that is because it will be the thermodynamic product. If you have a reactive eyelid, this will normally produce, okay, this will normally produce the cis, okay, because cis would then be the most, probably the easiest to synthesize, but we don't have the mechanism for that. So just know that trans islets produce, resonance stabilized islets produce trans compounds, whereas reactive islets produce cis, or cis is prepared by reactive islets. Now you might tell me, what is a reactive islet? A reactive islet is something that is not stabilized through resonance forms. Okay, remember you have charges, and the charges are gonna be very, very reactive. Okay, and the charges are gonna be very, very reactive. So, this is, as I mentioned yesterday, this is a small summary of the carbonyl groups. Okay, these are the reactions, so please do ensure that you have a good understanding of most of these reactions. Maybe not all of the reactions, but most of the reactions. Okay, because this is going to be very, very, very important. So you have reduction of carbonyls to alcohols, you have the Grignard reagents, you have the Clemmensen reduction, you have the addition of water to hemiacetals and acetals, okay, and thiols. So these three here. Then you have the addition of thiols and amines. Then you have addition of, apologies, secondary amines, okay, to form enamines. Then you have the reduction, the Wolff-Kishner reduction, addition of nitrites, and you will also have the Wittig process. After this, you can go and produce carboxylic acids if you oxidize aldehydes, and you can add nucleophiles. Apologies here. This is additional, this is tautomerization. You also can add halogen, which we haven't covered in this chapter, through the iodoform reaction. And you will also, you can also add more than one oxygen, so the iodoform reaction will actually continue. You can add an R group using a strong base, or you can do the aldol reaction or aldol condensation, or you can do, of course, depending on what you have, the Cannizzaro reaction. Okay, so for today, I will stop this video here. I might actually send you another video. I want to go and check through the syllabus to make sure that we're not missing much. And I will check through the syllabus to actually see what do you need to know for the rest of the syllabus and not. If there is anything that is quite short and I can fit it as a video for today's lecture, I will. Otherwise, I will leave everything for next week. Okay? See you, take care, and have a good day.